now let's, the last thing we saw is that this general proof idea is useful to do amortized proofs, right? So if you have a lot of equations with a proof, you can kind of do this, you can do it using these techniques. But what if you don't? What if you really just, you only have one thing you want to prove, you don't have a thousand things. You want to prove one. Can you do something? And this is, the common scenario, really. You just want to do one proof. And like I said, no, you really don't know of a way to use those techniques to do something better. And the reason is, the problem is that the challenge space was very small. And the reason it was very small was that it had to be, at some point we were multiplying the vector s with the challenge c. So if the vector s is over the integers, the challenge c just must be an integer. Otherwise, you cannot really multiply, right? Multiplication doesn't work. Okay? And the challenge also had to be small, right? Because we wanted the output, the z, to have small coefficients. You cannot have a large challenge. So the challenge c should be small and come from a large space. And this is really just impossible when c is in the rings, right? There's not a lot of small numbers. You can actually, know exactly how many small numbers there are. Define small, and that's how many small numbers there are. Okay? So you want maybe some ring that has a lot, that sort of can have a challenge c that's small, yet come from a large space. And that's exactly what these polynomial rings have. So the idea is you work over larger rings that have many small elements. So instead of integers, work over the ring of integers, which is zx mod x to p plus 1, ring of integers of some whatever that means, and you don't really know the algebra either. But, so here's an example. So you would normally work with a larger thing, but here's a ring z17x mod x to the 4th plus 1. So the elements of this ring are polynomials of degree 3. So what that really means, this thing, is that it's polynomials, but whenever you do operations, multiplication, addition, you always do it mod 17, and also mod x to the 4th plus 1. Right? So the reason it's written like this, I don't know, there must be some historical reason why it's written like this, but yeah, it's really mod 17 and mod x to the 4th plus 1. Okay, so addition of elements in this ring is really just coordinate-wise addition of polynomials, mod 17. Multiplication is the usual polynomial multiplication with an indeterminate x, but followed, mod 17, followed by a reduction mod x to the 4th plus 1. So if you've never seen, reduction modulo polynomials, it's exactly the same thing as reduction mod q, the exact same idea, right? So what does reduction mod q means? It means that q is really 0, right? So pretend q is 0 and write down, and pretend that 17 is 0, so, 18 is the same as 1, because 17 is 0. And same thing here. X to the 4th plus 1 equals 0. So whenever you see x to the 4th, replace it with minus 1. Okay, so here's just an example, if you really have never seen this. If I want to multiply these two polynomials in our ring, right, then I first do the usual polynomial multiplication. So I get whatever I get. And then I start doing the reduction. Right? Now, well, x to the 5th is really x to the 4th times x, so x to the 5th is really the same as minus x, so I replace x to the 5th with minus x. And there was no x cubed, so I just write this down. So then I reduce it, and it's this. So this is the multiplication in this ring. So now, the important thing is that when you do this reduction, mod x to the 4th plus 1, the coefficients do not increase that much. I mean, they can only increase because, by they can only double in a way. So maybe we shouldn't say do not increase. It's not quite correct. They can double. Right, but there are some polynomials where really you can have a small polynomial, reduce it mod that other small polynomial, and then the coefficients kind of grow exponentially. Right, so, but x to the 4th plus 1 is very nice, right? So anything plus or minus 1 is very nice, and that's what people like to use. Okay, so now we're going to define this ring cis and ring of the Lie problem, which I just simplified by saying it always can be written as AS equals T, because it really can be. by defining it the same problem, not over the integers, but over the polynomial rings. Right? So now, so you can do it, right? It's just multiplication, because before we were just doing multiplication addition over z, now we're just doing multiplication addition over this polynomial ring. All right? So now, but the nice idea is now the dimensions of A can be divided by D for the same belief content. So at least we don't know, if you work over the ring Zx mod x of D plus 1, you need the dimension of your A to be D times less. Kind of the number of integers is the same, if you think of it like that. And really, we don't know any better algorithms for the most part for ring system that ring over E, maybe. Yeah, I don't think we do actually. That sort of take advantage of the fact that we're not working over integers, we're working over polynomial rings. And now the big advantage here, right, why did we start doing all this, is that now the nice thing about this polynomial ring is that it has a lot of elements with small coefficients, right? If we just care about elements with 0, 1 coefficients, it has 2 to the d of them, right? Whereas before, if you want to compare apples to apples, the integers, if you want to look at the coefficients that are less than root n or something like that, whatever you want, there's only that many of them. Yet here, there's exponentially in d many. Right, so that's the nice thing for zero-knowledge proofs, where this is useful. The challenge space can be large and have small elements. Okay, so now just some notation. If we call this the ring, so instead of the integers, we have this ring. Now we have this ring mod Q, so that's our Q, and now B is going to be the subset of R with coefficients between minus B and B. Right, so that's just notation. All right? So now the zero-knowledge proof over R works, again, in exactly the same way as before, but now the big difference is the challenge space is bigger, and we don't have to repeat. But there will be a slide. Okay, so let's see. So we take y. So I'm not going to sort of keep track of how big y has to be. We know how to compute these coefficients to make sure that this rejection sampling doesn't lead to a large rejection rate. So let's just call it beta, and you can compute it yourself. So you choose y from like beta plus d to the m. So you can choose from some small subset. The coefficients are not too big. You send the w. So then it sends a challenge. So now this means it sends a challenge in the ring with 0, 1, minus 1 coefficients. Okay, and there is actually 3 to the d of 1. Okay, so the challenge space is large. And now z is sc plus y, as before. Now the multiplication is done over the ring, as before. And if z is not in beta to the m, send sort of abort and restart. So again, exactly the same thing as before, but now we're doing over the ring. And here he just checks if az equals cc plus w, just like before. And that z is in, or beta is something, depending on m, d, and m. Okay, so correctness and honest verifier zero knowledge is just like before. Nothing has changed, we're just working over a different ring. But now extraction, something slightly different happens. So the good news is that because the challenge space is big now, 2 to the 3 to the d, the prover must be able to answer more than one challenge, right? So we don't have to repeat many times. So then he extracts az equals tc plus w, az prime equals tc prime plus w. And the proof of knowledge, the extraction works exactly the same way. You have a times z minus z prime divided by c minus c prime is 2. But now, there is a different problem, that before, where the challenges were always 0 and 1, the difference was going to be 0 and 1, minus 1, 0, 1. But now, the challenges are some polynomials in a ring with small coefficients, but their inverses are not small. The inverse of a small polynomial is not a small polynomial. So now, even though z minus z prime is small, the quotient is not. So now you've again extracted a useless s. So, this does not prove that I know a small s, so that as equals 2. So we don't have that. So for rings, we kind of have, we have the ring size is big, you can really do an extraction, but you don't extract small s. But you do get something. Like, let's forget this is useless, but you do get something non-trivial. Like if you don't do this division, you do get A times something small equals T times something small. And that's actually good enough for some things, like signatures and commitments. And a few other things, but signatures and commitments, it's actually practical enough to be used in other practical things. All right, so here's what we can do, basically, with this interactive protocol, which was a proof of knowledge of something small, so that A times this equals T times something small. The original thing was just AS equals T. I needed an S to do this protocol, but I ended up proving something deeper. I ended up proving that I know some S, AS equals T times, not just T, but T times something else. But actually, that's okay. So we're going to use this for signatures. So here's the digital signature via the Fiat-Shamir transform. So, before I was doing interactive proofs, but of course a digital signature is non-interactive, so the prover kind of has to play the part of the verifier as well, but we can't trust him to play the part of the verifier. He has to send the challenge after the first round. So there's the first round W, and then he gets the challenge, right? So we have to somehow enforce that the challenge comes after the W, and this is the Fiat-Shamir transform in the 80s, right? So the prover starts with, or the signer in this case, doing exactly the same thing as before, sending the W, and now the C is not sent by the verifier. The C is computed as the hash of the W and the message. Okay? So because the W is in the hash, it sort of makes the order of the things the prover does just like in the original protocol. Okay. First he has to pick a W, then he picks a C because C is hash of W. Okay? And then he sends Z equals SC plus 1. So WCZ is the proof. That's the non-interactive proof in the random oracle level. It's a standard Fiat-Shamir transform. And then the verifier checks that AZ equals TC plus W, and that Z is in bigger. Okay? So now, to prove zero knowledge, right? To simulate the signer with an unknown random T, you can do it on this verifier zero knowledge proof, right? So if you recall how we did the simulation, we never knew S, right? So for any T, you can do a simulation. Same here. With an unknown, well, not an unknown random T, with a random T for an unknown S, this is our usual honest verifier zero knowledge proof. And the extraction is very similar. If you've seen, how to extract with a random oracle, it's kind of the same. So this is kind of not what I want to cover. Okay? So basically the security properties of this are exactly the same as in the interactive protocol. All right, and then what you obtain is A times Z minus Z prime equals T times C minus C prime, right? So that's what you can extract. So why is that okay? Well, because, before that I want to say that you can kind of, you don't have to send WCZ as the proof, you can just send CZ. That's the standard trick, and because he can recover, because WC and Z, once you know two of them, you know the third one. So you only need to send two, and W is usually much bigger than the others. Well, Z you have to send, but W is much bigger than Z. Okay? So that's what the signature looks like. Very basic. And now we want to show that breaking the signature equals solving some hard problem. So this is our A. So we wanted to, we have this A, and we append to it a T. So suppose that there is an adversary who can produce forgeries. He can do these proofs without, he can just do these proofs. Okay? So now we have an A, and we append to it a random T. And now it actually looks like a correct key, right? Because by LWE, AS looks random. A and AS, you cannot distinguish it from A and T, a completely random T. That's the LWE problem. Okay? So now this looks random, even though I don't know an S here, maybe there isn't even an S, but it still looks random to any adversary. And now, because what I'm going to show is that what we can sort of see is sort of almost the construction is that if you have A times Z minus Z prime equals to T times C minus C prime, then you can write it like this, and you have A times Z minus Z prime plus T times C minus C prime equals 0. And that's actually cis. That's the cis problem. So by LWE, A, and T, this looks completely random. And by cis, this is hard to obtain. So if there is a forger who can, or a malicious prover, who can sort of come up with his ZZ prime, CC prime, or sort of come up with forgeries of a signature, I can extract from him a solution to cis, assuming LWE is fine. Okay, and the simulation is done via the usual honest verifiers. So basically this, even though we couldn't quite extract what we want, it was good enough for signatures. Okay? So some other notes, we can also get homomorphic commitment schemes with zero knowledge opening, and this is actually important, it's used in the next section. So we can get basically commit, and I'll sort of go into more detail what we want from that. I won't show the construction, but you can do it, and it's very similar techniques as what I described. The digital signatures can actually be made very efficient. So the public key is, 1.5 kilobytes, signatures are 3 kilobytes. So it's really, we're not talking about megabytes anymore. We're really talking about somewhat bigger, not too much bigger than RSA signatures. And there are other ways to do rejection sampling. So this rejection sampling was the technique of only sending the Z if it doesn't reveal anything about S. There's more interesting things you can do. Sort of, there was a good question at the end of Chris's talk about why are we using Gaussians, and the answer was there's nothing special about Gaussians. They just make things work out tightly. You can use any distribution. So here, kind of again, for some reason, Gaussians can. If you make the distribution that you want not uniform, but Gaussian, you can kind of do square root of the dimension. You can reduce the size of the coefficients of it. It's not as good, it doesn't quite get as much savings as in the other case, but still, again, Gaussians kind of come in here as well. Okay, so this is kind of all I want to talk about for this technique, and I will then move to like the problem that we actually started solving. That we really have an S with 0, 1 coefficients, and a T that AS equals T, and I really want to prove that I know that S, no cheats, no factors of C here, no bigger coefficients for S. I think that is what I want to prove, right? Because for discrete log, that is what we could prove. We knew an X, GTX equals H. We really proved that we knew some X. We didn't prove some funny, weaker statements. So can we do the same thing for lattice, right? So this is what I want to cover next. And the answer is you can, but it's going to be less efficient. But now it uses different techniques, and sort of that research is just starting. I think we could get somewhat better there. So I guess someone has questions about all the previous stuff. Maybe now is the best time to ask. Okay. Yeah. Sorry? Yeah, still we don't know how to do that. Yeah, but the problem is there's something that T is getting multiplied by this C, so we don't know how to get rid of that C very efficiently. I mean, there are some ways to do it less efficiently, but it's still always, you're going to pay some factor. Like in the proofs, a factor of 10, and there are other techniques. Okay, but yeah, again, we don't have a better proof for that. Okay, but I mean, this will be but it'll be longer. It will prove this, but it will not use the same techniques at all, and it will be a longer. Right. So for signatures, we don't want to do it this way. We won't want to do it this way because the other thing was enough. But if sometimes you really want to prove this, and there are cases you do, then that's what you have to do. This is what you have to do. So, now we're going to need some more notation. So for vectors S and T, I'm going to define this component-wise product of two vectors as just the component-wise multiplication of their respective coefficients. Right? So you have you have vectors s and t, and s component-wise product with vector t is just s1t1, s1t2, s2t2. So that's just one notation. And now, the one thing we should notice is that coefficients of s being 0 or 1 is exactly the same thing as the component-wise product of s with the component-wise product of s minus 1, where 1 is the all ones vector, being 0. Okay, these two conditions are exactly the same. Okay? So we're going to be proving this. So instead of saying s is 0, 1, I'm going to be proving that s component-wise product of s with s minus 1 is 0. All right. So as a building block, I will need something called homomorphic commitments. Let's just pretend we have them for now. So what they're with zero knowledge proofs. So let's say we have a commitment for vectors s and t over some field, fp. We have a commitment to s, commitments to t, which is big S and big T. So I'm going to think the outputs of the commitments are going to be capital letters. And I want the usual properties of commitments, hiding and bounding. Right? So that commitments should have, they should not be revealing s, and they should be binding to s, but I also want homomorphism, right? So I want just additive homomorphism, nothing fancy, nothing FHE. So the opening of s plus t should be equal to s plus t, right? So that's the property that I want. If you add two commitments, the opening has to be the sum of the two messages. Right? So this sort of directly implies, as you can do this opening many times, that for all elements of FP, opening of C times S is CS. It's just because if you open S, open of S plus S plus S plus S plus S, C times. Right? So that's why this is implied. And we need to have a fairly practical zero-knowledge proof of knowledge of homomorphic relations. So basically, I have to prove to you that, oh, actually, I do know an S that, so first I have to be able to prove that, yes, I do know an S, so the commitment is satisfied. So this proof of knowledge is very similar to the techniques we did before, so I'm not going to talk about this. Let's pretend we have it. And I can also prove to you that if you have two commitments, or three commitments, let's say S, T, and U, that the opening of S plus the opening of T will be the opening of U. So that the sum of the messages in the commitments really is the message in the third commitment. Okay, so we have the practical zero-knowledge proofs for these relations. So let's just pretend we have such commitments. Yeah. Here. So just one more. What do I want to prove? The property I want from the homomorphic commitment. So I'm not going to, okay, so what I want is, let's say I have S, T, and U, and I want to prove to you that I know that U is really a commitment to what S committed to plus what T committed to. Okay? And this you can do. Okay? So now let's pretend we have these commitment schemes, and now I'm going to give a proof over them. So here's the prover and the verifier. Okay? So the prover kind of starts off very similarly to before, but it's actually very different. Okay? It just looks kind of similar, but really the reasons we do stuff is not quite the same. So you choose a random y, no longer small. A random y is good enough for some reason. And then you have w equals a times y. All right. So then we're going to do lots of other stuff on skipping for now. Where we're going to end up sending w, getting a random challenge, no longer small, a big one is good enough. And then z is going to be y plus cs, and I send z. Okay? So, but there's a lot of other, right now, this proves nothing so far, but there's going to be a lot of stuff going on. All right. So, now let's just focus on this, and now let's make a key observation. The key observation is, if you do the component-wise product of z with z minus c times the all ones vector, and where z is this, I'm going to expand z. This is y plus cs, that's just c. This is z minus c1 is y plus cs minus c times 1, which I can write as component-wise product y plus c times s minus 1. Okay, so far I did nothing, I just rewrote z. Okay, but this, now the key step is this one, the key observation is here, because now if you just write out the, expand or whatever, write out, you get something like this. C squared times S component y with S minus 1, plus C times something here, plus y squared. Okay, so if your S is really 0, 1, then this first term is going to be 0. Okay? If it's not going to be 0. So basically, if S times S minus 1 component-wise is 0, then this polynomial will be a degree 1 polynomial. Otherwise, it's going to be a degree 2 polynomial. Okay, so that's going to be important later on. Let's call these terms, this y and y2s minus 1 and y squared, g and h. They are kind of garbage terms, we don't care, but we have to compensate for them. The thing is, it's g and h, we can compute here. We don't need the challenge for that. I mean, the challenge will come in later, but this y and things that depend on y and s can be computed here. Okay, we already know them, and then maybe we can send something about them. All right, good. So, here's what we're going to want from our proof. And if we can actually prove this, then we've proved what we want. But that'll explain in the next step. All right. So we want the verifier to be convinced of these three things. First, we want him to be convinced that AZ equals W plus C2. So this is actually quite easy. That's like the only part that he will be convinced of this, but none of this is small. So this by itself doesn't prove anything. Then we want him to be convinced that this Z really is Y plus CS. That it's really, here it's just that's what the honest prover will do, but a dishonest prover may not do this. But we still somehow want to convince the verifier that no, really, this Z is Y plus CS. Okay? So I mean that's not trivial to do. Let's see. And we want the verifier to also be convinced that the component-wise product of Z with Z minus C1 is really C times G plus H. So we're going to send them something about G and H, and we want them to be convinced that this is really CG plus H, which would imply that this part is 0. And that should prove that S is. So let me kind of go into more detail as to why, if the verifier is convinced of these three things, that's enough to prove that S is 0, 1. All right. So why is this what we want? Right? What's the reason? Okay. So now let's do 1 and 2. 1 and 2. So 1 and 2 will imply that. So using rewinding, the usual thing we've been doing. This you can extract Z and Z prime, which are not small. A times Z minus Z prime equals C minus Z prime times 2. Okay, so that's, I hope by now you can see this. This is the usual thing, rewinding, extraction. Now this, if you write Z, if each Z really is Y plus CS and Z prime is Y prime plus, Y plus CS prime, plus Y plus CS prime, then Z minus Z prime equals to C minus C prime times S. Okay? And now, if you're convinced of this, then you have AS equals 2. If C minus C prime is a verb, but it's a field, so everything's equal. Right? So if you have these two equations, you're convinced that AS equals 2. But that's not enough because you don't know that S is 0, 1. So that's what these two equations are. If you know that Z is Y plus CS, and the component-wise product of Z and Z minus C1 is CG plus H, then I'm gonna claim that this actually implies that S component-wise of S with S minus C1, with S minus 1 is 0. And here's the reason. And this actually follows from the Schwartz-Ziffel lemma, but forget if you don't know what this is, it's fine. So suppose that this is not 0. Okay? Suppose that for contradiction this was not 0, this is something else, some R. Then the component-wise product of Z with Z minus C1, as we saw before, is going to be C squared times R plus C times some G prime plus some H prime. This is not going to be 0, right? Just by expanding because we're convinced that we know that Z equals this, Y plus CS, so we just expand it like this. But like the Schwarz-Zippel lemma says that the probability, so basically the Schwarz-Zippel lemma says that most simple thing is, I guess, well, you don't really need that. You just use the fact that a degree d polynomial has only d roots, right? So the probability that you will guess a root is d over the size of the field. So basically, the idea here is that if there was this r, then the verification here, right? So c squared r plus cg prime plus h prime equals cg plus h. If r wasn't here, then g prime and h prime are just g and h. So this is clearly true. But if there is an r prime here, there is an r here, then the probability that you can actually satisfy this equation for a random c becomes just 2 over p. So it becomes sort of small depending on p. Right? So if the r wasn't here, g prime and h prime is g and h, you're done. I mean, that's, you can satisfy, the prover can satisfy this equation. If r is not 0, there's this c squared part that gets in. And now what's the probability that c squared times r equals this? Well, that's going to be 2 over p. Okay? So that's sort of why proving these 3 things is enough to prove that that s equals s has 0 on coefficients. But we haven't proved them yet, right? We just think this is what we want to prove. Okay? So let's see. So now this is what we had written before. So now how can we convince the verifier of that? And this is where all these commitments will come in. So the first thing you want to do is you want to commit to s, y, g, and h, and send them over with the first step. So I'm going to send, so I obviously cannot send s, y, g, and h, because that would reveal things about s, but I'm going to commit to them and send them over. Then he sends me the challenge to verify. And now I compute z's y plus cs. And then I start giving zero knowledge proofs that I actually computed z correctly. So first I'm going to give a zero knowledge proof that I know an s that opens to s, I know a y that opens to y, I know a g that opens to g, I know an h that opens to h. And then I'm going to prove the relations. I'm going to give you a zero knowledge proof that z really is the opening of y plus cs, and that z times z minus c times 1 is really the opening of cg plus h. So this is where homomorphic commitments come in. So I never prove things, I never show things in the open, but I give zero knowledge proofs of just these relations. Right? And these are okay. Right? So I do that. And then I send all the proofs along with the z that I showed in the previous slide over. And the verifier verifies this. And then he checks all the proofs. And if he's convinced of all the proofs, then it implies these 2 things, right? Then really from this one you get that z really is y plus cs. And from this one you get that the component-wise product of z with c minus c times 1 is really cg plus h. So he proved that he really can open all the commitments and the homomorphic properties of this. Okay? So now some observations is that this challenge c that we used, has sort of is used in 3 distinct places and needs to have some algebraic properties that's sort of consistent with all these 3 places, right? So first it's used here, then it's also used in here. So here it's being multiplied by, so here it must be in the field in which we want to have 0 coefficients, right? Because we multiply it, we sort of add it to the z, right? And then here it must be compatible with multiplication with s, so it needs to have this algebraic structure. And then it also has to be compatible with multiplication by the commitments. So kind of all these fields of the commitment, fields of s, and where s is and where and this product, they have to be the same field, right? So you need a commitment scheme that really can satisfy this. So this is you can use lattice-based commitments, and this is kind of work with ourselves and the authors of this paper. Some of them are here. And so the commitment scheme that we use is this commitment scheme we have with Chris and with other people. So the commitment to a vector M is you have these public vectors B1 and B2, and the commitment to M is B1 times a small r, and then B2r plus the message M. So, and this commitment has all the required homomorphic properties, and you can do 0 1. Okay, and now the interesting thing is that before we need the challenge space to kind of have small elements, but now we don't care. The challenges in FP are in FP. So we don't need the challenges to be small because we don't prove the smallness of S by looking at C. We have other things, we prove it another way. So now C can be quite a bit larger. It can be, you know, as big as Q or P. Well, before I use Q, now I use P, but it's the same. Okay? So, so that's good, right? And now I'm going to show you some other things you can do, and this is using sort of general sort of PCE stuff applied to lattices. This sort of work in progress is basically proving cis relations using read-solved commitment. So this is the kind of ideas from the PCB world, but you can really use it for proof this. And it's pretty good for amortized work. So, and it's roughly the same size as when using lattice commitments for proving single instances. So if you wanted to prove one instance, the previous thing is almost as good. If you want to prove many instances, this is going to be much better. Okay, so so it's going to be smaller when proving several, even if they're unrelated, right? They could be for different AIs. I have A1, S1 equals T1, AK, SK equals TK. I can still do that, right? And so, and if the A's are even the same, then concretely you can do it even better. You can do it asymptotically sublinear, which is not impressive because, you know, with PCPs you can really do logarithmic, but sort of in practice, you have to be careful, but here you can actually do it very, very small in practice. Okay, so I'm going to briefly describe how this works. So give a very high level. Okay, so basically the key component is linear codes and commitments, and this is, you know, based on work that dates back to the 90s by many people. So the idea is this: let's say you have a matrix G, just a linear code that gets multiplied by the message M and some randomness R, and you get W. So I'm going to try to construct the commitment scheme. So you can forget that there are codes. I'm just going to try to construct a commitment scheme and show that why some ideas don't make sense. So this commitment scheme is binding and homomorphic. Okay, so it's clearly homomorphic because it's just multiplication. So to commit to M, I'm going to create randomness R, multiply G with MR, and give you a number. So it's clearly homomorphic because it's a linear relationship, and it's binding because it's binding because the length of W is quite big. So there really is a unique M and R that lead to this number, right? I don't even need G to be very long. I just need it to be invertible like this. Okay, but it's not a very good commitment scheme because it's not high. Because given W, you really can recover M and R. So that's not good. Okay, so second idea is, all right, I'm going to compute the W, but I'm only going to give you a small part of it. Right? So my commitment is I first pick my M and R, compute G times MR, compute the W, but now I'm like, okay, if I give you too much of W, you're going to recover M and R, so I'm going to give you a very small part of it. Okay, this commitment is still hiding. It now is hiding, so now it's actually hiding, perfectly hiding. And it's still homomorphic, because this part, if you keep revealing this part, you can do homomorphic operations, but the problem is it's not binding. Because if you give out an X, it's easy to find, it's easy to kind of complete the W to open it to any M. Okay, so this is not good. So what you need is kind of linear codes with PCPs, with probabilistically-checkable proofs. Okay, so the idea is you have to do something interactive, or non-interactive in more. Okay, so the prover commits to a W. So it computes the W. Okay, computes the W, and the verifier only asks for a small part of W. So the prover doesn't know which part of W he's going to ask, and it could be, here it's a contiguous thing, but it could be this position, this position, this position, this position. For simplicity, I'm just going to write it like this. So he asks for W. The prover asks for some coefficients of W. The prover sends it. And now, from this, the verifier should be somehow convinced, I'll explain this later, that this is really part of a code. This is really part of the W that the prover computed. So let's say he is convinced by that somehow. Then you can, that this actually proves that he knows that this really is binding now, because you can keep rewinding the prover, and he gives you different parts until he gives you enough parts that you can reconstruct him. So you only need a few, you don't need to know the whole W, you just need to know enough parts, and once you know this, you can reconstruct that. Okay? So you never send, the prover never sends the whole thing, he only sends a small part of it, but if you keep rewinding, you can get more of it, but you have to somehow be convinced that what he sent you really is part of the same W. Okay, so that's the key part, right? So if we can do this, if we can do this part, but that's the big question, how do you do it? How can you convince that the X's you keep sending really are part of that same W? Okay, so the idea is this. So you don't just tell him, I promise it's part of the same W, you actually commit to all the coefficients of W with a hash function. So you commit to this part, this coefficient, this coefficient, this coefficient, and you send the whole thing over, possibly in a Merkle tree, right? So you don't want to send all of these guys, that's too much, so you send a Merkle tree. The verifier, so we do that with this, so now the prover kind of picks this W, right? And now the verifier asks for a small part of W, the prover sends X, and now the verifier can be somehow convinced that this is really a part of W, because the prover can open those coefficients, because he has the hashes, the verifier, right? So now that you can say, okay, the prover is going to say, look, this is X, this is really X, and I'm going to prove it to you because I'm going to open these commitments. I'm going to send you, you can really check that this is what I committed to. Right? These really are the coefficients. Okay, so because he sent this guy. All right. So he's convinced that it's part of some W, but it still doesn't prove that this W is a code word. I proved that it really is part of something. I did have this in mind, but was this really G times something? Right? So the verifier is given Y plus CS, and he's given the randomnesses, the sum of the randomnesses, and actually, and the Z, and I want to convince him that really this is a code word. So he knows that these two are code words. He knows that this is a code word, and I want to convince him that these two are code words too. And actually, there's a lemma that says that if for a random C, the sum is a code word, or near a code word, then the original things must have been code words as well. So this is again kind of the same trick as this Schwarzschild cycle. So if C times S plus Y for random C is equal to Z, which we know is a code word, then S and Y must be with high probability also code words. So that's how you prove that the commitment when I committed to S before, so when I called it M, really was a valid commitment to something. Okay? So, I mean, the proofs are not trivial, I would say. I mean, to get them really, really tight requires a lot of stuff. But this was all done in the 90s. Maybe actually more is done now if you really want to compress the commitments. But anyway, the most expensive part of the proof is the hash. Right? It turns out that sending these hashes is very expensive. But you can do something, right? So the prover needs to send all the hashes of all the code words that he will commit, of all the coefficients of the commitments, and then prove that he's opening the correct slots. Right? So the way you do it is you put all the hashes in a Merkle tree, send the root in the first step, that's a commitment, and then every time you have to open some coefficients, you send the path, you send the leaf, and prove that this leaf really is in the tree. So you send the path. Right? And but that turns out to be the most expensive part. So I mean, people have been trying to do this, and I mean, there's lots of trade-offs, but really this is going to be around 100 kilobytes, and probably more depending on what other things do. There's tons of trade-offs here. So this, turns out to be fairly expensive. And but the nice thing is, even if you have many instances, you can you can reuse, you can hash them all together, right? So you still send the same number of openings of the tree, and that's the most expensive part, but that doesn't grow because all the leaves now contain, instead of just hashes to one thing, they contain hashes to all the things, and that doesn't matter, right? You still need one tree. So that's why amortized this is better, because the tree size does not grow. So this is basically this idea that if you want to prove several unrelated instances, you can use this because the tree size doesn't grow, and actually this is better, and fairly efficient. So of course you can always do something generically using PCPs, but that may not be super efficient. But this is fairly fast. And so this is kind of how you, right? So because you can reuse the hash. And if the A's, this is very different techniques. If the A's are all the same, you can do something even better. So that's the kind of idea. But this is really work in progress now. Like my students can do even better for single instances in this, so it keeps moving. But I don't think we can go. We will never. These proofs will never be as efficient as those approximate proofs for rings that I showed you before that lead to approximate signatures. You will always have something. I mean, it will not be, I don't know, 50 kilobytes or something like that. 30, maybe, amazingly, 30 you can do, but it's never going to be this 1 or 2 kilobyte thing where you have the signatures. But still, for other primitives, for more advanced primitives, this may be what you need. Okay. So, just some parting words. So, lattice-based signatures over polynomial rings are practical. So, signatures you can do lattices. And actually, I wrote up some, I had to write something up, so I just had to put on my webpage for how to construct these efficient web-based, lattice-based encryptions or signatures with many optimizations. Because a lot of the annoying part of lattice constructions is these little optimizations lead to factor 2 improvements, factor 4 improvements, but they're really important in practice. So I sort of brought that up, so you can search for it on my webpage. So work on exact zero-knowledge proofs for SIS is, I think, just beginning. I think you can do some interesting stuff there. Maybe you can have another commitment scheme, because we kind of only know one commitment scheme we're using, and then there's a standard PCP one. But maybe there's some other nicer commitment schemes that we can use. And maybe, maybe we shouldn't use the codes from PCP. Maybe we can have some lattice-based things there, but it's unclear. So these are all things I really don't know. I won't even guess what the answers to these are. But I think lattice zero knowledge really, it really is picking up, because just the progress in the last 2 years, we went from sort of being able to prove AS equals T with the proofs for a couple of megabytes using these generic Stern type techniques, and now we really I think we really got them down to under 100 kilobytes. So it's really a fairly significant thing, and it's still kind of going up. And for amortized, it's even better. Whereas before there was nothing.
Okay, any questions here? Also, we can after offline, right? It's offline. So let's thank that again.